All right, so today we're going to wrap up chapter two. We just have one important topic to cover, and that is something called implicit differentiation. Let me show it to you right here. Oops, sorry, that's three. Um, Here we go. Okay, so it turns out implicit differentiation is actually an extension of the chain rule, which we've already seen. It's just a little bit unusual the way it's set up. So, first things first, we need to distinguish between the words implicit and explicit, at least as far as functions are concerned. And so, the first thing you'll note here is that they've got two examples. The one on the left, implicit form xy equals 1. Let's write these down. And the explicit version would be y equals 1 over x. So what's the difference? Well, I mean, algebraically, of course, they're the same thing. What's different about the two is that here we have y is on the left and x, all the x's are on the right. Okay. And of course, that's what we're always aiming for when we set up any kind of problem that we want to work on. And on the left, you notice that's not the way it works. Both the x and the y are on the left. Okay, so you're probably thinking, well, what's the big deal? We'll just divide both sides by x, and that's true. But there's going to be many cases where it isn't feasible to algebraically separate out the x and the y. Okay, and in those cases, then we need to use this technique we're about to introduce, which is called implicit differentiation. Okay, so if you can break the equation up in the normal way into y on the left and everything else on the right, that's fine. You should probably do that. But if not, then the techniques we're about to use are what you would want to do because it's really the only option you have. All right, so how does this work? Um, oh, here we go. Here's one. Now, if you look at this thing, x squared minus 2y cubed plus 4y equals 2. Now you can see both the X's and the Y's are on the left-hand side. Now, again, it wouldn't be impossible to get the Y's isolated on the left, but I think you'll agree it would be very tricky. So what we're going to do instead is use this technique. Now, it's going to change the way we approach the derivatives, though, because um, differentiating Y is going to be different than differentiating X. So how are we going to do this? All right, well, here's some simple examples we can do first. So if we have a very simple case of, let's say, x cubed, we can use our old friend, the power rule, and we're all set. All right. As a matter of fact, that gives me an excuse to maybe do a quick review of some of the more important rules that we've seen so far. The power rule is applied to simple cases like this one. All right. So this one, we like this rule. It's very straightforward. Then we also have, we came across the so-called constant multiple rule, which looks like this. And then the next rule is implied by these two rules. The book refers to it as, they give it some name which combines the two, but these two give us the following result. Okay, so far so good. Now, the next thing we're going to do is remember how the chain rule works. And if you remember, this one is used for composite functions. Okay, so if you have a case like this, you'll end up with f prime of g of x, g prime of x. Or if, let's just say that you're using different notation, then, but this is just different notation. It's the same rule. And then we also have this general power rule that we went over. Now, what's interesting about this rule is that if you start here, you can think of this as a special case of the chain rule. Okay, so the chain rule is the more general result. This is a specific case. It's specifically designed for simple cases like this, u of x to the n, but it's taken from the chain rule. Now, this one also has an equivalent alternative way of writing it. The book shows that you also could have a case like this. They like to use this notation for some reason. I don't know. I'm not that crazy about it, but because it means the same thing. So in other words, don't forget u prime is the same thing as u prime of x, which is the same thing as du dx. I don't know. I kind of like this setup up here, but they often use this approach. So we have to keep our eyes open for it. So anyway, let's go back to the slides and you'll see that look at this very bizarre case. All of a sudden, we're trying to differentiate y instead of x because we're unable to separate it out, as we mentioned earlier. And so what happens here is that you can think of um, u of x is y is u of x. Now remember, y is a function of x. It's always understood that y is a function of x. So we're going to write it as u of x, okay? And then using the general power rule, if you have something like this, but and that's true, but because it's y in this case, in other words, y cubed is that function. We're going to have 3y to the second and then dy dx. Okay. So in other words, this is our u of x. This takes the place of u of x in the general power rule, and this takes the place of du dx. Okay. So that's that's in a nutshell how this works with implicit differentiation. Now, we're going to need to practice this quite a bit. It takes a while to get used to this, even though we're still technically using the same rules. Um, I still think you'll find that it's a little bit unusual to say the least. So, and by the way, also, I do want to point out one more thing. So you could write this as 3y squared dy dx, but sometimes the book will sneak in one of these. Dy dx is also written sometimes as y prime, as you remember, and you might end up with a result like this. And it means the same thing. Okay. Wow. Oh, that was kind of wild. So, I believe we have another example here that we can look at. Actually, let's see what their first example is. I like to build this up in stages. Sometimes they have a tendency to jump right into the very complicated examples, I've noticed. But these are good. Let's try these. Just to get used to this whole idea of implicit differentiation. All right. So now, of course, all the rules that we know still apply here. What will be different is the results of differentiating the y terms with respect to x. That's where we have to use the chain rule or the general power rule. Okay. So now here we've got a sum of two terms. We can break it up into a sum of derivatives. We can, here we're going to just factor out that three. Whoops, that's not what I meant to do. All right. So we know that the derivative of x with respect to x is just one. Over here, dy dx is just dy dx, and that's it. So that is our final result. Okay. So now what about the next one? Now this one's a little bit more challenging because you can see it's going to involve the product rule. Yes, it is. Okay, so let's remind ourselves how that works. All right, so I'll write it in two equivalent ways. All right, and then we also can write it like this. Anyway, sometimes the book uses one or the other. So the bottom line is that the way to remember it, no matter what the notation is, you've got the first function, and then you multiply that by the derivative of the second, and then you've got the second function and the derivative of the first. And that never changes. And so if you're thinking about it that way, you'll avoid getting confused by the notation. That's my opinion. Okay, so here we go. XY squared. What do we do with it? So we have the first times the derivative of the second, which is 2y to the first dy dx, plus the second term times the derivative of the first. Okay, so it's the same pattern. First derivative of the second, but using implicit differentiation, it's not just 2y, it's 2y dy dx. That's the unique part. This is what's new to this compared to what we've done in the past. And then down here we have the second times the derivative of the first. And then we just simplify it, of course. Um, x to y dy dx plus y squared. And of course, that's just 1. And then we can write it a little differently than that. Let's try this. 2xy dy dx plus y squared. And we're done. All right. And that's exactly what they have. Okay. Now, this one is a little different because this is actually an equation. We're not just differentiating one, an expression like we did here. We're actually solving an equation. Okay, so this is what they're giving us. There we go. So basically, what we're going to do, as you would imagine, is we're going to differentiate every term with respect to x. And then at some point, what we're going to have to do is solve for dy dx. That's the ultimate goal. All right. So let's just, yeah, I mean, because it does say find dy dx, but that's the target. So what do we do? And again, don't forget, if you can separate the y's and the x's, you should probably do that. It'll be easier. But here, I don't think that's going to happen. So let's try this. Well, all right then. Now there's nothing less for us to do except go ahead and solve for this. So now, as far as these y terms go, let's go back and remind ourselves when we did this for the first time. Let's copy all of this just to see how they compare. Okay, so here we have, as a matter of fact, actually, well, that worked out nicely. It's y cubed again. So they're reminding us how that works. 3y cubed. Um, sorry, not y cubed. Y, let me move this out here. It's 3. It's not 3, it's 2. It's 3 minus 1. Okay. So remember, we are assuming that y is a function of x, and therefore dy dx takes the place of du dx when we write out the general power rule. So that means that when we differentiate this, let me write it in more general terms. You've got n y cubed. Well, that's n. Let's see, how could I do this differently? Well, actually, I have a better idea. Let's do it like this. Let me just identify each of these terms. Okay, so it's the same thing. You can see that we're applying the general power rule, except with y instead of u of x. That's the only real difference. So the bottom line here is that for y cubed, we end up with 3y to the 3 minus 1 dy dx. And that reduces very nicely to 3y squared dy dx. Okay, now that's just the first of many terms. We also need a y squared. So based on the same setup, oops, when we apply this to y squared, it should be clear that you're going to get 2y to the 2 minus 1 dy dx. And that reduces to 2y dy dx. All right, so here's the first term, and here's the second. All right, and what was next? Um, Negative 5y. And then this one we can factor out the negative 5. Now keep in mind y is the same thing as y to the first power. And this one reduces to negative 5 dy dx. Okay, beautiful. Now, what else do we have? Oh, negative x squared. Now, negative x squared is a function of x only. So we can just use our normal rules, the ones we're used to. That'll be a nice change. Negative x squared. So we can factor out that negative if you want. And then we just use our old friend, the power rule. So we end up with negative 2x to the 2 minus 1, negative 2x. Then we get a break here too, because on the right-hand side of the equation, we have the derivative of a constant, which of course is just 0. All right, so now we gather up all of these pieces. Um, so I'll tell you what I'm going to do. Must be giving you a headache scrolling up and down so much. So I'm going to copy this so you can see it better. Now, this is one of the drawbacks of doing it this way. I mean, on the whiteboard, I've got so much space. Here, I've got very little space. So we'll just gather up everything we just did. That's the left-hand side, and the right-hand side equals 0. I just about have room for that. Good. Now, here's the thing. We'd like to get the dy dx's all on one side of the equation, and that's pretty much what we have. We're so close, but what we're going to do is get this 2x on the right-hand side. Now we can factor out that common term of dy dx. And now we can just divide out what's in the brackets. And that's it. We're done. That was a lot of work. I think you'll agree, but it worked. And yeah, 2x over 3y squared plus 2y minus 5. Okay, let's see. What else do they have? Now, they also, if I remember correctly, brought out some graphs here. This one in particular, is such a convoluted mess. I was working on it earlier and I decided, you know what, it's just too much. We'll be spending 10 or 15 minutes with this, and it's not going to give us any more insight into what we've been doing. But you can run through it if you want, but God, what a mess it is. The chance of making a mistake with something like this are pretty high. So I think we'll skip over this one and move directly on to something more straightforward like this one. Okay. Yeah, I mean, it was a nightmare. I don't know why they have to do that. All right, so let's try this one. I tell you, let me do this instead. Let me just write it directly and then we'll simplify it. I want to be completely consistent. D dx of negative y to the seventh, and then that equals d dy of 9, which is, of course, just 0. All right, so let's try this. Now, the first term is x. We know how that works. Use the power rule. Beautiful. And then for the 7x, same thing, just 7. Then we have 6xy, which means the product rule. All right. Now, once again, like we saw before, um, we're going to use the product rule. So what do we have? 6. We'll multiply by whatever we find here. So we have the first term times the derivative of the second, which is just dy dx, and then the second term times the derivative of the first. Now, technically that's dx dx, but we know that it's just 1. So we can just rewrite that as y, and then we multiply everything by that 6. Okay, so that's that term. And then we also have negative y to the seventh. So we'll factor out the negative. And now remember how this works when it's y, negative, and then we're applying the general power rule. Okay, so we need the dy dx here because of the general power rule, and that's all you need to. It's basically u, one more time. And of course, now the u to the x is the function that we're dealing with, but it's a function of y. So you've got 7y to the sixth dy dx with the negative sign, of course. Okay. And then we also had 9. Okay, so that's clearly just 0. So just like before, we'll gather up all these results. Where is it? Yes, there we go. And then we'll get our answer. All right, so we ended up with all right. So we had 4x cubed plus 7. Then the next one was 6x dx dy dx plus 6y. Although I haven't multiplied it out yet. 6x dy dx plus 6y minus 7y squared to the 6 dy dx equals 0. And like the last case, we're going to move to the other side of the equation any terms that do not contain dy dx. So we have negative 4x cubed minus 7 minus 6y. And now we can factor out the dy dx. All right. And that should do it. Now, this is a multiple choice. So, they may have moved the negative on the outside there. Let me just rearrange it slightly to line up with what they're doing. Yeah, let's see. Now, if we factor out a negative from all the terms, we'll end up with this. That's good because that leaves us with C, which is the correct answer. Yeah, sometimes it's a question of lining it up with the way they wrote it. We had it right. It's just that, they rearranged it slightly. Now, the next one is a little bit trickier because what they want us to do is not just do implicit differentiation, but we have to find the equation of a tangent line to this function, whatever it is. As a matter of fact, just out of curiosity, let's go into Symbolab. You can imagine trying to graph this on your own without, I mean, it's just look at it, the way it's written. Oh, what am I doing? Look at this, x squared over 2. Okay, let's try that again. Y squared over 98. Sometimes it gets a little stubborn. Equals 1. All right. Well, I mean, it's pretty clearly an ellipsis, except that it's a vertical ellipsis, and they're asking for this tangent line at the point 1 comma 7, which would be roughly around here. Now look at that mess. Okay, so let's try it. So the first thing we're going to do is just use implicit differentiation, just like before. That hasn't changed. Okay, let's do this. So what we're going to have to do is take the derivative of every term. All right, well, two of the three terms will be very simple. The first term is a function of x squared, so we'll just use our old friend, the power rule. First, let's simplify a little. And the right-hand side is just 0. Okay. Oh, sorry, I did not use this notation correctly. That's better. Okay, so we'll have 1/2 of x 2x to the first power plus 1 over 98. Now remember, this is a y term. We must include this dy dx after we apply the general power rule. So we end up with x plus 2 over 98 y dy dx equals 0. And then we can simplify a little bit. Here we've got 1 over 49 y dy dx. So we subtract the x from both sides. And I'll tell you what we're going to do. Let's rewrite this slightly. It'll be a little neater like this. And what I'm going to do is divide out both sides by that y over 49. Now, if you remember, dividing by a ratio is the same thing as multiplying by the inverse. So we're going to have negative x times 49 over y. So we have dx, a dy dx is negative 49 x over y. But we're not done yet because we still need to find the equation of this tangent line, which they chose the point 1 comma 7. So first we find the slope. So we plug in x and y. So yeah, x is 1, y is 7. Okay, great. So we have the slope. Now, this is the tricky part. We know that the equation of a straight line looks like this. Fine, we don't know the intercept. This is sometimes called the slope intercept form because those are both included in the equation. But there's an equivalent version we can use instead called point slope form because, first of all, you can see it contains the point x1, y1, and the slope is m. Well, we know the slope and we know one point. So we just plug them in. And then we solve. And we got a result. Okay. Negative 7x plus 14. And that would be C. All right. So that's that. All right. So now here's what we're going to do. This is 2.5. So what I've decided to do, I'll mention this right now. In the interests of time, we will skip 2.6. Okay. It's an application involving volumes of cones and that kind of thing, which I think that it may be one of the least important topics in the whole course, and there are no assignments based on it. So I think maybe we'll just not go over that. You can read it if you want, but it's not going to appear in any of the assignments or on the exams. So it'll be an optional section. All right. Then that means that the next time we meet, which will be very soon, of course, the next session will be the start of chapter 3. Now, this is an important chapter. This is one of the most important chapters in the course. That's why I'm eager to get to it. I want to get started. I'm going to skip over the 2.6. You can read it if you want. This is important. In fact, it's almost impossible to overstate how important this is, um, because this is our first introduction to something called optimization, which basically means finding the maximum or minimum value of a function. Now, it's something that we do all the time with applied calculus. When you're using calculus, like imagine yourself running a business and you want to find out the optimal number of units to sell to maximize your profits, this is what you're going to do. Or find the level of output that minimizes the cost of production. That's the kind of thing that we'll be doing in chapter 3. So it's awfully, awfully important. So the next time we meet, that's what we're going to cover. Chapter 3, optimization methods. Now, I don't think they use that term in the title, but that's what we're actually doing. Okay, so it's a fairly long, involved chapter, so that's why I want to make sure we have plenty of time for it. So we're done here, and next time we meet, we'll do chapter 3. So I'll see you then.